and B, source geology.
There we go.
At Cardiff University.
Yes.
Excellent. Then he went on a non-funded research position at the British Geological Survey. So you can see he's coming from geology proper, but then honed his data science skills in industry, which I think is very cool, before moving on to a PhD here in Exeter. That was EPSRC and Met Office funded. You can see with the Met Office, it goes slightly further towards the weather. And I think the idea was, and I think that worked out quite well, to predict the weather even better than the Met Office already does, using data science and statistical techniques. And I think that is generally the kind of where it's going, right? Combining data science, stats to do better probabilistic models, which we all love. And now we have him, that is fantastic, on board for IDSAI as a research fellow with us. So you guys can collaborate. And so we are really glad you're doing this talk, because it also means that people get to see what you do, except and not just what you can do for them, but what you do in your other part of your research fellowship. So I hope you enjoyed the talk. We only got a glimpse from it at the panel, and I loved it, so I hope you will too. Thanks. I'll let you get on with it.
Thanks. Yeah, the introduction sounds great, but yeah, and so will the talk be. But I think it just gets me realizing that like it's been 10 years since I graduated originally, and then if you keep doing stuff, then you end up having an intro that sounds like you've done a lot, which is great. Anyway, yeah, so this is the talk, and I need to flip these screens. Well, maybe I won't bother. Or does someone know? You know, at the moment, isn't it on like annotate?
The big screen.
Bottom right, yeah.
To make it maximize.
Yeah.
Sorry, I should have done this already. Thanks, that'd be great. Anyway, this talk is basically about what I've been doing in applying, well, data science to geology, which is my background, as you know now. And I know that probably, maybe none of you are actually geologists here, but you're kind of going to have to imagine that you are, because I originally presented this to the Geological Society of London. I published this article in their magazine, which is proven to be, well, quite popular, maybe a bit controversial, but also quite popular. You can pass this around. There's a post-it note. Okay, you've seen it already. Yeah, so I did this work that got on the front cover of the Geological Society magazine. This is the talk I made to kind of explain it to the Geological Society, who were all geologists. And so you're not geologists, but that's okay. You just have to imagine that you are.
It was up, but now it's not.
Okay, yeah, it was.
But before it went quiet, it was just up. So.
Anyway, that's all right. I just can't remember where the button is. There's a button to swap.
Yeah, it says from the. There you go, from the beginning and then it can't.
It doesn't matter. I'm not full screen, but that doesn't really matter, does it?
Online, interestingly, you are.
Oh, that's interesting. Well, anyway, it doesn't really matter. Anyway, okay, so yeah, I'm Charlie Kirkwood. Those are pictures of me that I have my online profiles, where if I do this talk for people who only know me online, that's how I guess they know me, but I think most of you know me in real life, so the pictures don't help much. You've already had my introduction, so I won't worry too much about that. I want to thank my PhD supervisors, who have all been very helpful. This is them. The kind of geological mapping work was a kind of a late stage spin-off of what I've been doing for the PhD, which is kind of going back to my roots, I suppose.
Charlie, I think we might, sorry, I have to interrupt you because I think online it's not advancing, the slides are not advancing.
Okay.
I think we might have
Charlie, so click on the toolbar at the bottom, click that thing on the far right of your open windows. No, like, no, left. You see
all right, an open window.
You see your
do you just want to, you can come and do it.
Yeah.
Like, so I think what's happening.
Sorry, it was working earlier.
I mean, this is just a guess, but I think you have it open in full screen. It's just, it's here, I think.
Ah.
Oh, maybe not. Well, no, you're, okay. You're,
Thanks.
Well done.
So now if I go through the slides, hopefully everyone, including people online, can see.
Yeah.
Okay, so I've already said what the talk's about. It's a talk about artificial intelligence and its importance to geology. And I told the geologist I didn't want it to just be another data science talk, because I think there's a lot of data science talks about various aspects of, I guess, specific applications in geology that you could use artificial intelligence. But this, I think, is like the big one, because it's geological mapping, which I'll explain a bit more in time. So this was the AI map, and obviously I'm going to talk about this in more detail, but to give a bit more background, this is like brand new, and no one's kind of ever mapped geology like this before. So it's new and no one was used to seeing it. This is like a ternary map of the concentrations of potassium, iron, and calcium in red, green, and blue. But traditional geological maps, including current geological maps, have always been these hand-drawn things where geologists basically make observations in the field and they'll draw polygons around basically bodies of rock that they kind of deem to be sufficiently similar to be able to class it as a particular unit. So everything is like discretized, polygons with no kind of variability within them. And you can also see here, if you can see, like there's various places in this map, and I could point out more if there's time at the end, but often like different geologists map different tiles just based purely on like the British national grid. And then different geologists will disagree. So you end up with basically these like vertical or horizontal lines in the map where things don't even match up. And this is like Britain's official geological map. So it's kind of an issue. And to give more height to geological maps and why they're important, this is basically text I just took off the Euro Survey's website, and they are a consortium of all the geological surveys in Europe. And they say that geological maps are the language of geology. And if we imagine all the fields of the geological sciences, for example, mineral resources, geological hazards, groundwater, geoenergy, and many more, if we imagine all of those as the chapters of a book, geological maps and models would be the language in which the book is written. So you kind of can't get around it. Geological maps are like the thing in geology. It's kind of what ties together all the observations we have and all the little sort of point-wise analyses that we have. Geological maps are the thing that tie it all together. Okay, so part one of this talk, which is in 3 parts at different lengths, is about the past and present of geological mapping. So you may have seen this timeline before because I think I've used it before, but this is, I think, a really nice just kind of image to show how technology has advanced in the last 200 years, and specifically it's got a bunch of climate science advances. But I think it's just really nice to remember how quickly things are changing, basically, and how much has changed. In 200 years, a huge amount has changed. So it was in 1815, which is just over 200 years ago, that William Smith, who was sort of the father of geological mapping, basically, he published the first geological map of Britain in 1815. And that was like the first national scale geological map anywhere in the world. So like the history of geological mapping stems from exactly this point. And 5 years later, there was another person called George Bellas Greenhoff, who published a second geological map of Britain. And George Bellas Greenhoff was the president of the Geological Society of London, which was formed just a few years earlier. And interestingly, William Smith wasn't part of the Geological Society of London because he was kind of an outsider. I think he sort of wasn't part of the aristocracy, so he kind of wasn't included, but actually it was his idea to make this national scale map. And then it's sort of widely accepted that George Bellas Greenhoff's map was kind of a rip-off of William Smith's, although it was a bit different. They'd chosen different things to emphasize in their classification. So William Smith had used like fossils, and George Greenhoff had focused on mineralogy. So it's like 2 different things that you could use to make those classes. And then another thing that's interesting is that in 1835, it was called the Ordnance Geological Survey back then, but that's when what is now the British Geological Survey was founded. And that's a bit like the Met Office for rocks, like it's the UK's provider of geological information. And so dating back to this time, and William Smith, who was the father of all this, basically, there's a quote by him from 1839, which says that the principles of geology, like those of geometry, must begin at a point through 2 or more of which the geometrician draws a line, and by thus proceeding from point to point and from line to line, he constructs a map. And this has been like, well, that's like the motto of geological mapping. This is what it's been. And now over 2 centuries later, 2 centuries, it's a long time, our geological maps are still hand-drawn, basically, only now we draw them on a computer screen instead of on a piece of paper. So this is like the current state of geology. And I've been referring to this all as classification first mapping, and no one's emailed me to say that that's unfair or anything. So I think like it's kind of accepted that what we've been doing is classification first mapping, by which I mean this act of drawing polygons on the map. The polygon, each polygon is a class, so you're drawing like class boundaries. But yeah, you're going straight to the classification rather than trying to map like the underlying properties, which I'm going to talk about a lot more. These are 2 examples of classification schemes that are used to decide like what to call a different unit of rock. So for example, here on this axis is like sodium and potassium concentration, and this is like silicon concentration. And within that space, these different kind of, well, polygons again, like represent different rock types with different names. So it is kind of buried within the system of classification first mapping by drawing polygons, that the polygons should mean something in terms of these kind of continuous properties that underlie the rock types, which can be like composition like these ones, or it can be age, texture, it could be a whole bunch of things. But basically there's all these properties behind the scenes that until, well, basically we just sort of ignored them, I guess. So we've just been drawing polygons. And that's classification first mapping. So you could say, if it's not broken, don't fix it. But as you can guess, I guess, from the fact I'm even giving this talk, that's not really my view. Because it's got some quite significant flaws, this traditional classification first approach. And the main one, I'd say, is that well, it suffers from not being directly comparable with reality because the different classes don't predict directly measurable properties. As I just showed you in the previous plot, a class might have some kind of meaning in terms of the properties space, but it's kind of not a direct link. Like it's quite a woolly way of trying to map a property to say what class it comes from, I suppose. It's basically what it comes down to. And then that means that if you've got an existing classification first geological map like this, it's really difficult to say like how accurate it is, and it's very difficult to compare one map with another and say which one is better, because if it's just a bunch of these polygons that represent different rock types, but if it hasn't been explicit about what those measurable properties are that are being predicted by each polygon, then you can't really say what's better and what's worse. And so I think we've basically spent 2 centuries in this kind of limbo land where one person can propose a change to a map, but it's purely like opinion based whether or not that's better, because you can't get some kind of hard measure of actually what is better. And on top of that, the kind of traditional classification first approach, it just doesn't have any way of kind of capturing or conveying uncertainty. Like the geologist that draws the line might have some knowledge or some kind of idea of how certain or uncertain they are, but there's no real way of conveying that in these maps at the moment. So that's a big deal, because when people are using these maps to do things like, I don't know, they want to know what they're going to encounter when they're digging tunnels or whatever, if they only have one answer, which is the form of this sort of single map, then the chances are what they're going to encounter is going to be different, but they don't know how different that's going to be. And as I mentioned before, we've got these inconsistencies across map sheet boundaries. And all of this is quite low fidelity because of the nature of this kind of discrete way of mapping what is fundamentally a continuous geological system. So basically the kind of maximum accuracy that you can hope to achieve is limited by the number of different polygons you've got. And you could say, okay, let's just map with like 1 million polygons to try and get closer and closer to the truth. But that just becomes really kind of ugly. It's not very neat. So there's quantization error in making all this in discrete classes when maybe you could do it continuously instead. So this is like a kind of conceptual example in a profile of, or transect rather, of what it kind of equates to when we've got these classification first maps, and what that might mean in terms of like the properties that are predicted by those classes. So if you imagine that this line here is just yeah, this transect across part of the map here. And then each different polygon here is like shown as a different line here that represents a different class. But because the polygons are like flat, basically, when you think of them in terms of what they might predict in terms of properties, that means that basically that they're attempting to represent continuous geological properties with just a blanket answer that's just flat. You just say, well, it's in this unit, but that's it. It's not a prediction of the actual geological properties. So then around this, if you want to use these maps to predict anything that you're interested in, which might be like the concentration of precious metals or something, if you're exploring, maybe you're trying to find like lithium for batteries, something like that, or you want to know how strong the rock is because you're trying to build the foundations of a building or something. At the moment, kind of the best you can do would be to try and like post-process these polygons to kind of dress them with some distribution of what the values of those different properties might be. But this isn't built into the map, but like the map is just the polygons, as I've been saying. So on the one hand, you've got uncertainty about how the kind of data is spread around those polygons. And on the other hand, there's also model uncertainty in the sense that actually the boundaries that separate these polygons, they could be in a different position, or like most likely they are. Like everyone accepts that there's error on where these lines are drawn, but the problem is that they don't convey what this error might be at all. So those are like two quite significant limitations of this, or the two forms of uncertainty that we should really be interested in, basically, which is like model uncertainty and data uncertainty. So is there a better way? And well, yeah, as you can guess, I think that there is a better way, otherwise the talk will be over and that'd be pretty boring. So yeah, my proposal basically is that we could shift now, or the technology is in a position to allow us to shift to a properties first approach to mapping instead. And this is a great benefit because properties first maps are then directly comparable with reality because they do directly predict measurable properties, such as the ones on which the classification schemes were originally based anyway. So this makes it much easier to assess map quality. For example, we can adopt the concept of likelihood, or the probability of our observations given the map. Yeah, which in this case basically means the probability that the scenario depicted by a geological map would produce the observations that we see in reality. And using the likelihood, as StatSci people in this room know, then enables basically uncertainty quantification by a Bayes rule, which then kind of paves the way, or more or less is a route directly into having then calibrated ensembles of geological maps as a way of representing uncertainty, which is basically quite a bit more like what weather forecasts do with ensemble numerical weather prediction. What else? There's other benefits too. Yeah, the maps are consistent. There's no map boundary issues anymore because you're just putting it all in one model, and this could potentially be on a global scale as well. And there's no artificial limits on fidelity because this would be mapping the continuous geological properties on which the classifications were based anyway, but mapping them as continuous variables. Okay, so if we put all that together, then you get what I've put on the front of the magazine, basically. And I think it almost is like going back to an alternative, an alternative timeline in a way. And instead of purely going on what William Smith was talking about back then, actually, if we look at what people like Pierre Simon Laplace and Thomas Bayes were talking about back then, really like the same period in time. They just never spoke back then 200 years ago. So Pierre Simon Laplace says that the most important questions of life are indeed, for the most part, only problems of probability. And well, I think that he's right, basically. And then you might say, am I not just talking about geostatistics in this whole talk? And the answer, I think, is kind of yes, but then also kind of no, because, well, at least in the geological world, people seem to really think of geostatistics as just being like kind of ordinary kriging, these kind of traditional, original geostatistical models, which are quite simplistic and involve making assumptions of like stationarity or isotropy, basically using like a stationary kernel with unchanging parameters through the space, which is potentially unrealistic when it comes to mapping geology, which is quite complex in reality. And on the other hand, there's sort of these techniques that have grown out of the machine learning or AI world, where the philosophy I think is a bit different, and it's more about trying to just develop methods for learning from like huge data sets and maybe having less restrictive assumptions in general, but of course still reliant on statistical principles. So maybe it's the case that, yeah, machine learning and AI are really being carried by statistics. So a kind of controversial opinion that I have, slightly controversial, although I don't know if anyone in this room is going to mind, but I kind of had this idea that the reason that we haven't moved on from like the traditional hand-drawn geological maps is because of this issue of seeing like geostatistics as being these kind of restrictive techniques like ordinary kriging that assume stationarity, for example, where that isn't actually appropriate. And I know that there are ways that we can deal with this and do things like kind of non-stationary kriging. But I think in the geological community, then people don't necessarily know about those techniques, or for whatever reason, one reason or another, it hadn't been done before anyway, at least to try and make like a continuous properties first map of Britain. So this is actually work that I did in 2016, which was comparing what the output of ordinary kriging might look like if you interpolate through the observations here are cerium concentrations in shallow soils, which is basically very indicative of the underlying geology. And yeah, so ordinary kriging is essentially using a Gaussian process to interpolate in 2D or 3D space. So if you look at that in cross-section, you get something that looks a bit like this, where you've got a smooth function going through the observations and then some kind of uncertainty intervals going around it. But then when you look at that as a map, because we're assuming stationarity, then the mean of that is a very kind of smooth thing and perhaps unrealistically smooth. And there's no information coming in from like other sources as well in like basic ordinary kriging. Anyway, so that was one example. But then, so what I did in 2016 was look at if we use machine learning instead and feed it with like other sources of information that we have available, such as satellite imagery and various geophysical surveys, then you can basically learn something that just looks like very much better, because it's capturing a lot more of the geological structure is the thing that I guess that matters. And you can do regression kriging, which would essentially do the same thing. I suppose here it's kind of like using, in this case, it was a random forest, using a random forest as the regression component and actually saying how much can we predict just from the regression component without even worrying about the spatial component. And if I click between them, then, well, I think it looks much better geologically, but also you can see that the fit of the model, like down here in these plots, it actually turns out to be better as well. So that's good. So it's only really recently, bear in mind, I wrote this for geologists, so I don't want to be patronizing, but yeah, I think it's only really recently in the last 10 years or so that a combination of like increasingly powerful computers and also some breakthroughs in like the efficiency of algorithms have made it possible to start making serious headway in geological mapping in the age of artificial intelligence. I think it is true that, yeah, more than 10 years ago, we probably couldn't really have been doing this, but I think now we can. And previously, technological limitations meant that we were forced to make geologically unconvincing assumptions in our models, or at least I think, yeah, the price of entry to go further seemed too far out of reach for most of us. So basically, I think no one was really doing it. But now things have changed very fast. So maybe everyone in the room knows, or maybe you don't, but back in autumn of 2012, that was kind of the deep learning breakthrough sort of happened then. Deep learning had existed for a long time before, but it was in 2012 that, well, Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton, who's quite famous, they sort of smashed the performance on this image recognition challenge called ImageNet. So that was the first time that using deep neural networks without manual feature engineering had been able to classify like general images of like household objects and animals and stuff. It had outperformed like, yeah, human manual feature engineering. So that was really exciting. And that was only 10 years ago. So the 10 years since then has been a really exciting period in terms of deep learning being like adopted and tried out in loads of different applications. So I was quite happy to have this deep learned map, geological map on the front cover of the Geological Society magazine in autumn 2022. So it only took, well, 10 years, yeah. I can't read the writing, so I can't read off my own slide. That's a shame. So the big question is, I think basically, are we now at a point where we can sort of go back? Historically, that I think there's kind of been two branches. There's been the traditional classification first mapping branch, which if you're a geologist, that's what you do. You draw maps by hand, like that's what you do. And there's also been geostatistics, and at least traditionally, that's been seen as these kind of stationary models, spatial interpolation, things that are not particularly great at capturing geological structure. So on the one hand, you've got hand-drawn maps that do capture geological structure, but don't actually give you a good prediction of geological properties. On the other hand, you've got things that can predict properties like smoothly, but not really geologically realistically. So I think the big deal is that now, are we at a point where we can actually bring the two together and have basically geostatistical models, but that actually make assumptions that are convincing to everyone. And so I see this as being the time that we can like unite the ideas of William Smith and whatever his name is, Greenough as well, with those of Laplace and Bayes at the same time. So then it would be really probabilistic geological mapping. So part 2 of the talk is understanding Bayesian deep learning through the example of geological mapping. Which if you were geologists would make a lot of sense, but you're not geologists. Sorry about that. You just got to pretend to be. Anyway, so this is really two different concepts, as I think probably most of you in the room know anyway. You can do deep learning and you can be Bayesian, and you don't necessarily have to do them at the same time. But in this case, that is what I'm doing. But first of all, I'll talk about the deep learning part of that, I suppose. So I have this paper that we published last year, which is called Bayesian Deep Learning for Spatial Interpolation in the Presence of Auxiliary Information, which is kind of like the machinery on which that article in the magazine is based. And this was basically a way of thinking, like, how could we incorporate structure from gridded covariates, like satellite imagery, for example, or even just from terrain elevation data, which is what this is, and actually that's what we used in this paper, how we can kind of learn useful features from gridded covariates in order to improve how we can interpolate through point sampled observations of environmental variables in general. And I think this is a really common problem, basically. I think it also applies to like weather forecast post-processing, where you've got like point sampled weather stations, and you've also got like gridded output from numerical weather prediction models. And if you could somehow kind of harness all the information in the gridded numerical weather prediction output, then that would improve your ability to, well, post-process weather forecast, for example, probabilistically, which is some of what I did in the PhD. But anyway, yeah, so it's about how we can learn structure from gridded covariates in order to improve interpolation through point sampled observations. And then the result of that here is to be able to produce these kind of nice maps that have a lot of detail captured in the structure of the covariates, and that also are well calibrated and good predictors, basically. So to do this, we have this deep neural network architecture, which is actually not all that complex in a way, but you could say that it's inspired by regression kriging in the sense that it combines basically a regression component with a kind of spatial interpolation component as well. But it's doing it all with, in this case, deep neural networks. So there's a bit more flexibility than traditional approaches. So to start with, yeah, we've got this part as a stack of convolutional layers, which ingests an image of the gridded covariate centered on the observation from which it's learning from. So this stack of convolutional layers is able to basically learn like features from the gridded covariates that are predictive for whatever it is you're trying to predict. So that's basically a computer vision component doing the regression part, if you were thinking of it like regression kriging. And then at the same time, in this branch here, then we've got basically a really wide layer of fully connected, it's a really wide, fully connected layer, which behaves approximately like a Gaussian process, which is then a bit like ordinary kriging. I think we literally could be using a Gaussian process there, but in this case, we're not. It's just neural networks. And then these two branches, the like kind of regression and the spatial part, get combined then in another couple of hidden layers, which are fully connected layers. And basically those end up outputting the mean and variance of a Gaussian distribution, so that this thing will basically give you a prediction as a Gaussian distribution, of whatever it is that you've trained it on. And yeah, basically in red is kind of like the global position being considered. And then in blue, all the stuff going on with the convolution, it's kind of thinking about local context. So if you've collected some observations across the landscape, then this kind of architecture is a way of combining information, a kind of global location, and specifically what's going on locally type of way. And so this basically forms our data model, where in this case, where we're mapping observations in calcium and stream sediment samples. So here, this allows us to basically like sample calcium values or sample possible calcium values from this normal distribution, where both the mean and variance are functions of global position and local context according to, well, the weights in the neural network. Yeah, and that's like a general thing. The general thing here, that it could be any y, it doesn't have to be calcium, and it's just saying that here we're predicting y using a normal distribution where the parameters are functions of x, but they're quite complicated functions because it's a deep neural network. So what does this look like if we think about it in terms of a transect? Okay, so we can imagine here again the same example that I showed earlier, where the red line here is a transect across the map. And yeah, basically here is drawn, for example, the true value of some geological property that you're interested in. But obviously in reality, we don't know what this is, but it does exist. Like there is a true value of this property, whatever it is. Let's pretend that it's shear strength of a rock or the rock. So we don't know what the truth is, but we wish that we did, but we don't. But we do have a finite number of observations that are measurements of this truth, basically. And they will have some amount of measurement error, which means that like they're not bang on the line, but they've got some noise, basically. So this is what we got to go by, a bunch of observations. And so then if we think back to this like neural network architecture, then basically we're saying that like the X, which is going along here, this is obviously just like one dimension in this very simple plot, but you can imagine it being like everything going in here. So it's positioned in space, but maybe it's also things learned from like the covariates as well. And then the Y is just the output, which in this case would be, okay, calcium concentration. Forget shear strength, we're still on calcium concentration. So the neural network's parameters or weights dictate the mean and variance of the Gaussian output as a function of the neural network's inputs. And every position on the map provides a unique input that the neural network translates into calcium concentration values according to the function dictated by the weights. So if we were to just like initialize the neural network with some random weights, then we'd find that the function that those weights dictate is already capable of giving us a prediction sample from a Gaussian distribution, like all across the map, basically. So you can like sample, just by initializing the neural network, you get like essentially like kind of random looking maps of just functions, but those functions are obviously not necessarily very good at this point. So different configurations of neural network weights, different values of W sampled from our prior distribution over weights, you could say, produce different models for calcium concentration Y as a function of X. Any of these neural network produced models for calcium concentration can generate pseudo observations at any point in space by sampling from the neural network's Gaussian output. And if you do that everywhere, then you get a map. So basically we've got like a data generating function. That's what the neural network is. But what's the probability that the observations we see in reality could have been generated by the model or map defined by W, and this would be the likelihood. And in this case, I think the likelihood is quite low because basically all the observations are quite a long way away from like the probability mass of the model. But instead of that, then we could aim to have a single best map, and we can achieve that with deep neural networks just by using optimization to maximize the likelihood. And then we might get something that looks like this, which is then like a pretty good fit through the observations, so arguably actually quite good. But at the same time, just going for maximum likelihood is quite brittle because maximizing the likelihood on training data doesn't necessarily mean that you've got good predictive performance on as yet unseen observations. which is the thing that actually matters. And maybe this is less of an issue if you're just doing, I don't know, some model without many parameters. Like if it's linear regression, then maybe you don't have to worry so much about this overfitting, basically. But with deep neural networks, you do have to worry about that because there are so many parameters that it can quite easily just kind of fit through your data points, basically. And this means that you end up with situations where, although this appears to be a good fit and it all looks quite confident and so on, but then actually when you compare it to reality, where you don't have observations, it can be quite far away from the truth. So instead, we should embrace this idea of the primacy of doubt, which is the fact that we don't know for sure what's happening between our observations, and aim to model a distribution of plausible maps instead. Again, I think everyone in this room is probably on board with this. So anyway, but you're not geologists, but even some geologists are. Okay, so then we get to Bayes' rule, which is basically the way that we can do this. So modeling a distribution over maps requires learning a distribution over the neural network weights W given the training data D. So we want to learn P of W given D, which would be this posterior distribution over the weights. And this is proportional to our prior belief about what the weights should be, which is just our P of W to begin with, multiplied by the likelihood, which is the probability of the data given the weights. And the evidence, which is P of D here, works as a scaling factor to ensure that the posterior distribution sums or integrates to 1, which it has to do to be valid. So the samples here, by the way, are basically from like deep ensembles, which behaves a bit oddly, if anyone's wondering why they look a bit potentially odd compared to what you're used to seeing from, for example, Gaussian processes. But on the right here, we've basically got like samples drawn from the prior, basically, of the neural network. Like you can, before you've learned anything, you can have functions sampled from it that would look like this. And then after you've learned something, you want to end up with this distribution of functions or data generating functions that actually are a good match to observations. And yeah, so to do that, we start with the prior distribution over weights, P of W, which produces something like this. And then you can actually get the prior predictive distribution, P of Y given X, by doing this integral here. So you're basically, for each possible arrangement of weights that you might sample, then you apply the likelihood function in order to have P of Y given X and W, and you integrate over that, and then you get P of Y given X. But that's the prior predictive distribution. If you want the posterior predictive distribution, which is P of Y given X and D, this is the data, then you basically have to do this learning in order to get the posterior distribution over weights, which is P of W given D. And there are some sort of oracle type people that will tell you that a Bayesian is calibrated if his or her probability statements have their asserted coverage in repeated experience. Basically, this makes sense because if you have a map, for example, and if it tells you there's a 90% chance of finding something at this location, then it makes sense that you would want that to be the case 90% of the time. And how can we assess that? Well, there's things called proper scoring rules, which people working in weather in this room would know about. And these are basically ways of assessing, well, the quality of a probabilistic prediction, essentially. So a scoring rule is proper if the forecaster maximizes the expected score for an observation drawn from the distribution F, if he or she issues a probabilistic forecast F, rather than some other forecast G, which is not equal to F. It is strictly proper if the maximum is unique. So basically, these proper scoring rules guide us towards predicted distributions that match the true distribution of Y, but which are honest. So like they're honest about their uncertainty. They get penalized for being overconfident. And a popular one here is the continuous rank probability score, which is the mean squared error between predicted and observed cumulative distribution functions. So this gets applied in like weather forecasting quite a lot, but in geology, people don't really talk about this, but it's just as applicable, I would say. So in what I've actually done, we've been using this approach called Monte Carlo dropout, which is something, well, kind of designed for deep neural networks specifically, and it's a way of doing approximate Bayesian inference. And it works by giving each node in the network a probability of being multiplied by 0, or dropping out at each iteration. So this means that it induces a distribution over the weights of the neural network, because each weight can either be, let's say, some non-zero value, or it can be 0 with probability P or whatever letter you want to call it. So that means that basically every time you every iteration of the network, or every time you sample from the network, you actually get a different configuration. Like it's a different function that you're sampling from, because it's got this distribution that it can either be 0 or the weights that the optimizer is optimizing. So this collectively induces a distribution over functions, which in our case here is a distribution over maps. And optimizing the weights of the neural network with dropout active means that we are not simply optimizing the likelihood of a single model or map, but actually optimizing the entire predictive distribution. It's been shown that the Monte Carlo dropout approach applied to deep neural networks approximates the posterior of a deep Gaussian process, and that's Yaron Gal and Zubin Garamani, who were both Cambridge people at the time and both cleverer than me, so you can ask them how that works, but I can tell you that it seems to work quite well in this case. So we can tune the dropout rate with the aim of achieving the best calibration on held out test observations so that our probability statements have their asserted coverage in repeated experience, which is what we want if we listen to people like, well, Andrew Gelman, but actually you don't need to listen to him. It's just, I think logically it makes sense. Okay, so now talking about the results from all this. So we remind ourselves that this is like what we're using to generate these maps, this deep neural network architecture, but using Monte Carlo dropout for approximate Bayesian inference. And one of the things that's interesting from a geostatistical perspective is to look at basically the variograms of simulations from the posterior predictive distribution here, from the deep neural network, that is, because basically traditional geostatistical models. Why is everyone looking like they're not paying attention? Come on, this is exciting. I think the problem is you're not geologists.
We're focusing really hard.
Yeah. No, good. Okay, good. Before maybe people might be falling asleep, which would be allowed, but this is like the best bit. So yeah. Yeah, so we've got these variograms, right, which is basically a way of modeling, or rather plotting. This is the semivariance here. So this is basically a measure of how different observations are, or no, just how different values are according to the difference between, or the distance between them, sorry. So logically, you expect that as distance increases, then the difference between values of whatever it is that you're mapping or that you've just collected observations of will be more different. Whereas when you come like to zero distance, then you might expect them to be basically not different at all, because by the time you're collecting a sample like here and here, then you're on the same stuff, so it'd be the same. But you still tend to have some amount of what you call nugget variance, which is basically just where even where you've collected samples like bang next door to each other, they can still be different due to measurement error, for example. Anyway, so the interesting thing is here that even though our deep neural network approach, like it has no particular parameter that is something like a length scale, even without that, it seems to be learning to be able to simulate maps that actually have autocorrelation properties really similar to the observations. So I thought that was actually, well, kind of a remarkable thing in a way, maybe something to be looked into further, but I was quite surprised that happens at all. Because the traditional geostatistical approach is you've got some kernel that have like a length scale, and then you're implicitly making predictions based on basically the autocorrelation structure of the data. But that's not what we're doing here, but we're still finding that simulations have similar autocorrelation structure to the observations, and that's all tested on held out test data. So each blue line there is the variogram of a different simulation, a different simulated map, basically, from the posterior predictive distribution of the deep neural network. And the red line is the variogram of the held out test observations. And they're all evaluated at exactly the same locations. So that's like a fair test. Okay, and then, so we can also then, I'm just flicking through here, and I hope you can see that the map on the right, each map now on the right is a different simulation from the posterior. And so they're all slightly different, basically. So each one of these maps on the right now is like as if it was one of the blue lines on the variograms there. So that's quite good. We can simulate basically ensembles of possible maps. And then that in itself, I guess, is only useful if you know that the ensemble is kind of well calibrated or accurate in some way, but then we can check that here as well. So these are basically the performance of these things on, well, on held out test data. So in this data set, which is actually quite big, we've got a held out test set of like 10% of the observations, which is still something like 10,000 observations. So this is really big. And so one thing we can do is we can just look at the mean of the predicted distribution and use that as if it was just a deterministic model, and compare then how well the observations compare to the predictions, or rather how well the predictions compare to the observations. and find that it's a pretty good fit. So the R squared is 0.74, which sounds pretty good. And the root mean squared error is 0.56, which sounds pretty low, which is good. And then we can also look at basically the kind of probabilistic calibration of these in various ways. Maybe the easiest one to look at here is basically this is a QQ plot. So we're looking at what proportion of the held out test observations fall below each of the predicted quantiles all the way from 0 to 100. And well, basically it tends to be, well, I don't mean it tends to be, I mean on the evaluation set or the test set rather, the held out test set, it's really seemingly very well calibrated, so that's also great. So now we know that it's quite good, and then you can start looking at the map and thinking, well, I don't know, what's it telling us that we kind of haven't seen before? And bear in mind that this is all kind of a new way of doing geological mapping to some degree. So, for example, these images here, which are taken from this like zoomed in red box here. So we got, originally we got the elevation there, then we got the predictive mean of log calcium, which is what we were predicting. And I think it's really cool to see, like, this is very, very detailed, basically. Like if you move a very short distance, then things change already because it's not just doing spatial interpolation, but it's learning from the landscape at the same time. And it's also seemingly very precise about where it's uncertain, basically. So again, if you move a very short distance, you can go from having, well, this is the standard deviation of the predictive distribution, and it just changes like very sharply through space, which I think is a good sign as well, because you want things to be well calibrated, but ideally you also want them to be sharp. And then this green line going from south to north. Here, then we can look at a transect of, well, predicted values from the model, and the gray ribbon on here is a 95% credible interval around the mean. So that basically gives you an indication of the model uncertainty, how much uncertainty there is between where the mean of that Gaussian would be. And then in the colored points are then just samples taken from, well, from the entire predictive distribution, actually. So if we look at where the points are, then that gives us like the total uncertainty of everything, but the gray ribbon is just the model uncertainty. And I think it's interesting to see that even with this like Monte Carlo dropout approach, which is maybe not the most sophisticated, we still seem to have situations where basically, like for example here, the model uncertainty seems very high, and so does the total uncertainty. But if we go over here, then actually, even though the total uncertainty is high, the model uncertainty isn't that high. So basically that varies everywhere. So we've got two different things, the model uncertainty and the data uncertainty, varying seemingly fairly independently through space. So that is basically an explanation of everything. And if you were a geologist and you'd seen the magazine, you would have been very excited to hear all that. But having not seen the magazine, you may not have cared that much, but I hope you cared a little bit. So the front cover of the magazine is basically implementing the same architecture, except that here I've just asked for like 3 outputs at once. So it's all learned simultaneously in the same model, but we've got separate output distributions for potassium in red, iron in green, and calcium in blue. And I think it's quite exciting to think that basically you could add many more different things here. These are just 3 element concentrations, but you could add measurements of strength of the rock or of age or whatever. And then somewhere in the middle of your neural network, or in fact at every level and to some degree, then you're learning like a representation of geology from which all the properties can be predicted, which is pretty exciting, and that hasn't really existed before. Yeah, and again, the front cover maps also basically validate really well, again, tested on the same held out test data. So I hope that this paves the way for the future of, well, probabilistic geological mapping, or just really to make probabilistic geological mapping more of a thing. And also, to be fair, there are people who do look at probabilistic geological mapping, but it's basically always been like classification first. Geological maps have always been about the classes. So I guess my point is to say, well, actually, with all the AI technology, we don't need to be restricted by classes anymore. Like we can shoot for the properties and we can probably get them, which is quite a lot more like weather forecasting in a sense, where you're predicting like values of continuous weather variables or weather parameters. And part 3, which is very quick, it's just literally one slide, is the implications of adopting properties first geological mapping powered by probabilistic AI. So we get much more transparency about the accuracy of our maps, and the uncertainty is quantified, which is good. Hopefully we get fewer nasty surprises for users of geological maps. It allows decision makers to be better informed by risk. So they can see like a distribution of what possible geological scenarios they might encounter on a project, rather than just telling them it's definitely this, which it almost certainly isn't actually. The model uncertainty, epistemic uncertainty, can be used to optimize collection of new observations, allowing us to maximize our knowledge of the lithosphere more efficiently. And this is a huge thing as well, because for 2 centuries, it's sort of been like, oh, you know, geologists might go over there and check their lines in the right place and might decide to move it a little bit or whatever, but then you couldn't really say, is that actually better or is that worse than it used to be? It's really hard to say, whereas now we can like quite specifically define some kind of accuracy measures and then just kind of optimize them by collecting new observations. So that's really exciting. I think it may allow us, if we apply this kind of globally, to achieve better outcomes in the climate crisis, because the lithosphere is an important part of the Earth system, for example, as a source and store of carbon. And our current classification first maps, I think, are basically preventing us from seeing the opportunities that we need to be able to see. And if you think about it, like our atmospheric models are very much more advanced than like lithospheric models, which are kind of, the geological maps are the lithospheric models to some extent. And they kind of have to catch up. This is how they can catch up, I think. And I think that will then mean that there's a lot more science we could do in terms of thinking about how the atmosphere and lithosphere interact, maybe, because we'll have the lithosphere in the same kind of detail that we're used to seeing in atmospheric models. So this will facilitate new discoveries, and it provides a way to unify previously disparate point sampled observations and analyses into a single model of the geological system. I think I kind of said this at the beginning, but a lot of what happens in geology is like a scientist will go somewhere, collect some samples, analyze them, say something about them, maybe, you know, date them using radioactive isotopes. So you've got these kind of, all these kind of point-wise analyses, but we haven't really had a way of kind of bringing it all together. And I think having a way to bring it all together will almost certainly reveal, well, just new kind of knowledge that we didn't have before, and that's a quite exciting thing as well. And use of probabilistic mapping opens the door to model averaging, whereby different individuals or groups with different prior beliefs can combine their models, improving prediction accuracy and providing a more nuanced understanding of uncertainty. I kind of put this in, well, I think it's true, but I put it in specifically for the geologists because I think, understandably, there might be a worry that if you say, well, we're going to migrate to AI geological mapping, and then that means immediately everyone's kind of like redundant because you've just got an AI system doing what used to be the job of whole organizations. But I think that's not really true because all of these models are fundamentally subjective because you kind of got your prior is different. For example, like my prior is like built into that neural network architecture, but someone else might have different ideas about what the prior ought to be. And there's no reason why we can't combine them, basically. So I think this isn't a reason why, if anything, it makes it more collaborative because then you can basically each have bigger models and combine them in a logically more sensible way than just meeting at a map boundary, deciding that you don't agree, and then having a mismatch for the rest of time in the map. Yeah, so we'd have no more mismatches across map tile boundaries, which is actually a good thing. Right. So thanks for listening. Congratulations if you're still listening. That was the talk. And look, it's just literally 3 o'clock right now. That's good, isn't it?
We have a few questions, even though it's 3 o'clock sharp.
Sure. I'm sorry. I should have said earlier then. Yeah.
No.
I'd like questions.
I think you put it there with a copy of
Well, yeah.
Yeah. So people might have time. But obviously, if you have to leave, don't feel shy to leave.
Yeah. Hi, Joe. Thank you. That was very informative. I just wanted to know whether you showed the RMS and the RMS error and the R² plots for your model. Did you make a direct comparison to a sort of Kriging-based interpolation method? and I understand it will be very difficult to make a fair comparison with the hand-drawn maps. It will be difficult to get out of sample data.
Yeah, I think with the hand-drawn maps it's more or less impossible. So I haven't made that comparison directly, but it would be interesting to do. But I think
we'll see if you were better. If you see if you were better, even though they've used all the data to make their maps.
Yeah, but I think the thing is, it is really difficult to get a prediction of a property from a hand-drawn map because they don't explicitly predict the property. So in order to have a prediction of a property, you have to post-process it in some way.
Okay.
So they're kind of unaccessible in my
definition for what is, I don't know, quartzite rock or whatever they're calling it. They don't have a...
Yeah, no, so they do have, like, they'll have named a unit and they'll have said this was deposited between approximately 300 million, 280 million years ago, and it would tend to be like a lithic aronite or something. But like, so then from that, you could go back to the classification scheme and say, okay, that's kind of like saying that we expect these properties, but there's nothing explicit about it. So it's subjective. It's very subjective. And the question about how to compare it to the traditional geostatistical methods, well, that is a good question. And actually, so I haven't done it in a very rigorous way, and so I didn't include it in the publication. But in my view, in a way, I think the best way to have that done would be for someone else to represent that side, because I think basically whatever I did, I'd be accused of straw manning like the opposition, which I don't want to be doing. So I basically just put out like my idea for what made sense. I think that well, from like the, let's say, preliminary experiments I've done, I think that it is better, but I would like someone to come forward and say, you know what, you're talking rubbish. Whatever, traditional geostatistics can do better than this, but it hasn't happened yet anyway. Yeah, thanks for the questions.
I've got a basic, I know nothing about geology question.
Yeah.
But all the properties you show like are on maps.
Yeah.
Doesn't it like very much like downwards as well?
Yeah, okay, yeah, that's a good question. I haven't really mentioned that. Or in fact, these models are just using, at the moment, surface properties, but I want to develop it to be subsurface as well. But yeah, you're totally right. They're maps, but I can't really show you, but basically, so yeah, they are fundamentally 3D, but we know more about the surface than we do about the subsurface. Like we only have quite limited observations of the subsurface from like relatively few drill holes, you could say. So the current methodology for having a 3D geological model is basically, they do these things called fence diagrams, where they take like a bunch of transects across the map and then draw a cross section of what it would look like at depth. And then by kind of interlocking these like different fences, then you get an impression of what geology is doing in the subsurface, but it's not like an explicit, it's not like a voxel model. But again, I don't know. The fairest way of me doing this talk would actually be to co-present with like someone who is doing the traditional method of mapping, because I don't want to be like straw manning the traditional way. Well, I don't think I am, because I published this stuff in that article, which like the entire geological community has seen basically, and no one's come back to me and said, you're talking nonsense. Anyway, yeah, it is fundamentally 3D. I haven't talked about that, but I want to incorporate it. But I think the same principles can apply, basically.
Also not a geologist. How random are the distributions of the input data, like spatially? Is there bias in sort of a distribution of the data going in?
Yeah, so I think the answer is kind of there is, yeah. So the middle plot here is actually, it looks blurry because there's so many of them. It almost looks like shading because there's so many of them, but actually this is like 100,000 stream sediment geochemical observations across the UK, which is what I used to make this map and the front cover map, basically. So it's not, yeah, like the sampling density isn't uniform across the map, which I haven't done anything specifically to sort of, I don't know, compensate for that or anything. I'm not sure how much of an issue that is. Anyway, that's what it looks like. Yeah, some of the rock types don't have many streams, like chalk in the southeast of England. I think because the water just sinks into it, you don't really get streams, so then they don't collect stream sediment samples. Anyway, yeah, thanks. Do you have questions, John?
Well, I thought directly to that, and that might just be how you do your example. At the very beginning, you had this example with the different hexagons overlaid onto the kind of observations. And that might just be, yeah, exactly.
Yes.
And it looks a little bit, and that might just be how you put your example, that there is more observations within the hexagon than on the boundaries.
Oh, I see. I think
is that a true thing?
I think it's just coincidental.
It's
just coincidental. In fact, the reality is that when constructing maps like this, basically geologists in the field you actually look for outcrops where you can see the boundaries between units, basically.
Yeah, because you would normally think people are interested in where to put the boundary for the hexagon, right? Not kind of go for the middle. But I mean, you could also say the middle is a secure place where you know what you should expect, right?
That's true.
It could have gone either way. So yeah, I mean, how much, in a related way, how much do you think from your map you can actually learn about places to look for things that people haven't looked for before because it was just not a known thing? So.
So I think basically if you just looked at a map of the model uncertainty, the epistemic uncertainty, then that would more or less directly guide you towards the areas that we don't have enough observations from. Because some places we don't have many observations, but they're actually very uniform in terms of their properties, so it doesn't matter. Whereas whereas there's other places where things change a lot more, there's a lot more complexity, and that's where we want to prioritize getting observations. And also these days, observations are a lot more sophisticated than they used to be. It used to be literally looking by hand, but then, so this data set, which I didn't even barely talk about, but actually it was way ahead of its time because they started collecting this geochemical data in the 60s, I think, something to do with exploring for uranium. I'm not sure what that was related to. Anyway, stuff in the 60s. Anyway, and they were collecting that from Scotland downwards for the next 50 years. I actually worked on the very last sampling program for it, which is quite cool. So that was just finishing off the south of England. Anyway, but there's lots of different data sets we have now. Of course there are, and the traditional way is kind of been for geologists to just look at these quantitative data sets, kind of mull them over and think about it, and then just draw on a map by hand. But obviously this makes more sense, I think.
I think the talk really interesting. I was just wondering, are you planning on trying any alternatives to MC dropout? Because like you said, that field right now trying to get uncertainty in Bayesian neural networks is huge. And you said, it kind of gained popularity because it was really computationally feasible as opposed to and you have so many good points about all the different types of uncertainty here, the uncertainty from the experts that might be being lost. And MC dropout is probably capturing kind of a specific kind of uncertainty in the architecture of the network, right? So are you going to play around with other ways that you can kind of capture these different sources that you totally know are there?
Well, I would really like to. The reality of it was I wanted to kind of make this happen, and I did try variational inference as well, I think, but I couldn't really get it to work, whereas Monte Carlo dropout just kind of worked. But I think that's the reason why it's popular, is because it just kind of works. It's easy to implement, but it doesn't necessarily mean I'm sure that it is not the best, but at the same time, I was quite pleasantly surprised by the results seeming quite good. So yeah, it's definitely something I want to test. I mean, I'm open to input. All this is set up as well, so in theory, you could just drag and drop a different inference approach into it or whatever. I mean, it's not that simple, is it? But almost. So yeah, I'd like to look at that. If people have got master's students or something that wants to do stuff like that, then I've probably got projects.
Yeah, good pitch.
Yeah.
We've got a question here in the chat.
Yeah.
Okay. Firstly, thanks very much for your interesting talk.
Thanks.
In your results on slide 73, your model seems to struggle to make accurate predictions for the very small observed values of calcium. What is your insight in for this behaviour?
Yeah, that's a good question and a fair question. I think that they're referring to, can you see the cursor? Oh, you can, that's good. Sorry, people online, I haven't used that the whole time. Anyway, yeah, there's a lot of observations that are basically, well, it's the log scale, so they're not zero, but if it wasn't log scale, they'd be very close to zero. The reason is, again, this was in some way me just taking actually a slightly simple approach, I guess. Basically, the geochemical data that you get out of the lab, it comes with a bunch of quality codes, kind of qualifiers. And one of the things it tells you is that basically sometimes an observation was below the lower limit of detection. And the kind of rule of thumb or a thing that people do in that situation is simply to give it the value of half the limit of detection. So that's what those are. It's where I've given them the value of half the limit of detection. And ideally, I probably would have, I guess, build it into the model to handle that kind of lower limit of detection. But again, it's a level of complexity added to the whole thing, whereas this work was really me just wanting to get something working so that I could try and persuade people it was worth pursuing.
Any other questions? Anybody mulling over a question? No, you're all good. Should we grab a coffee then?
Yeah.
Coffee sounds good.
Well, thanks very much.
There you go.